When we talk about AI, we usually talk about all the data it's fed. But there's this whole other side to it, a kind of secret control panel. A bunch of hidden settings that can make the difference between an AI that's a total genius and one that's a complete flop. So let's dive in and take a look at the knobs and dials that really control artificial intelligence. And that's really the big question, isn't it? We hear all about the algorithms, we hear about the data, but what about the foundational choices that are made before the learning even kicks off? These are the settings that actually define how the learning process is going to go, and getting them right is, well, it's part art, part science. I think this is the perfect way to picture it. Seriously, imagine you've got this super powerful, really complex machine. The quality of what it spits out doesn't just depend on the raw materials you put in. That's the data, right? It depends just as much, maybe even more, on how you've tuned all the little dials on its control panel before you even flip that on switch. Those initial calibrations, that's what we're talking about today.
Okay, so to really get our heads around this, we need to understand the two main pieces of the puzzle. First, there are the settings that we control. We'll call them the knobs. And then there's the learning that the machine does all by itself.
So first up, we have the hyperparameters. These are the knobs. They're the big picture rules that you, the human, set for the model. Think of something like the learning rate, which is basically how big of a step the model takes while it's learning. Or maybe the batch size, which is just how much data it looks at in one go. You decide all this stuff up front. Then, on the other side of the coin, you've got the parameters. This is what the machine learns internally. Once you've set your knobs and hit start, the model just gets to work. It starts crunching the data and tweaking millions of its own internal values, like the weights inside a neural network, all to find patterns. These are the things the model learns. You don't touch them directly. And this chart just lays it all out nice and simple. On one side, you've got the human operators setting those knobs before the training even begins, things like that learning rate. And on the other side, you have the algorithm learning its own internal parameters during the training, like all those network weights. The key takeaway is this: the choices the human makes are what creates the environment for the machine's learning to actually happen, or to fail. So, if it's just about setting a few knobs, how hard could it be, right? Well, turns out it's one of the single biggest challenges in all of machine learning. Now, what's really interesting here is that not all of these knobs are created equal, not even close. Research on a certain kind of network, an LSTM, for the curious, shows that some hyperparameters like the learning rate and just how big the network is have a massive, huge impact on performance. But then others, like batching and momentum, they barely move the needle. This helps us know where to focus, but it doesn't make the choice any easier. It's a tempting thought, isn't it? If a bigger, more complex network can learn more stuff, why not just crank that dial all the way to 11 and let it figure everything out? And here's the trap. This is what's known as overfitting. The model becomes so ridiculously complex that instead of learning the actual patterns, it just straight up memorizes the training data, every little quirk and bit of noise. It's like a student who crams and memorizes the answers to a practice test, but then completely bombs the real exam because they never actually learned the material. The model loses its power to generalize, which basically makes it useless. And to make it all worse, there's often no single right answer. Take that mini batch size, how many examples the model sees at once. Some published papers say the sweet spot is a tiny number, like between 2 and 32. But then you've got other super successful models that use batch sizes in the thousands. The best setting totally depends on your data, your model, your task. It's a complete moving target. But this isn't just some academic puzzle for data scientists to argue about. Getting these settings right has massive, real-world consequences. It affects everything from how reliable a model is to how safe it is. So the goal isn't just to get a high accuracy score on a test. It's about building a model that you can actually trust. And that means you need robustness, so it doesn't fall apart when it sees new data. You need reproducibility, so other scientists can check your work. And you need reliability, so you know its performance wasn't just some random one-time lucky break. And get this. This is how sensitive these systems are. A lot of models use a bit of randomness to get started. Well, it turns out that just changing the initial random seed, which is basically just the starting number for a random number generator, can completely change the final outcome of a deep learning model. If something that small can have such a huge effect, you can just imagine what a challenge it is to make these things truly reproducible. This quote really just drives the whole point home. If a model's success is super fragile and depends on a lucky guess of its settings, you simply cannot put it into a mission-critical system. No way. You would never want that kind of instability in a self-driving car's brain or a tool that helps doctors diagnose diseases. The stakes are just way too high.
Okay, so if finding the perfect settings is so incredibly hard, but also so incredibly important, how do people actually solve this problem? I mean, they can't just guess forever, right?
The solution is a process with a fancy name, hyperparameter optimization. But at its core, it's a pretty straightforward loop. First, you pick a combination of settings for all your different knobs. Step 2, you train the model and see how well it does. 3, you analyze that performance. And then, you loop back to step 1 and try a different combination, hopefully a little smarter this time based on what you just learned. But this isn't just random trial and error. It's a systematic search. The goal is to intelligently explore this huge space of possible settings to find that one golden combination, the one that gives you the best possible model by minimizing errors on the specific job it was built for. It's a hunt, really, for that perfect calibration. And that kind of leaves us with this final thought. We think of AI as this world of automated learning where machines just figure things out on their own. But as we've just seen, the entire foundation for that learning rests on a series of really critical choices made by a human. So it makes you wonder, even as our machines get smarter and smarter, how much of their success will always come down to the wisdom, the intuition, and the judgment of the person setting the controls.